Welcome to the introductory course for POSIX shell scripting. It is mainly intended to help you to efficiently operate some Unix-based systems by learning the shell programming language and using the shell scripts by finding out their strengths, their syntax, debugging techniques, and their main features, which make them such powerful programming tools. To begin with, we will discuss the introductory module. Our main objectives are to learn how a POSIX shell script is generated, to find out how the shell treats the command code, to understand how the shell effectively processes them, how the runtime context and external influences are affecting its execution and its output, how to create and prepare a file as a shell script, and we'll end up by looking at a main features list of the main Unix shell interpreters. What is, after all, a shell script? Simply put, a shell script is an executable text file containing one or more Unix commands. The code within such a file is made out of human-readable information. So shell scripts are programs, but they are directly executed with no compiling necessary. The POSIX compliant programs are, as their close relatives as well, acting as an interpreter for the ASCII text within the script and executes the commands contained in the file, one after another in their initial order. Most of the shell scripts are used to automate some task which may be repetitive or tedious or too time-consuming to perform manually. To be more exact, the shell scripting techniques derived from the need to process a particular kind of Unix processes, the serialized array of tasks which the system administrators call batch jobs. In the end, shell scripts can be one line or several thousands of lines in length, depending on what it is you need to do. Programming in the POSIX shell can be very simple once you master the standard Unix language. This course will help you to do that by providing plenty of hands-on practice with the POSIX shell and its built-in programming tools. But why scripting at all? In contrast with strong typed languages such as Java or C and advanced complex IDEs, which in turn imply considerably learning effort, the shell programming offers on-the-fly results, nice execution with shortcodes with minimal costs. They provide very powerful utilities, fully equipped system management applications written in shell scripting. Of the main benefits of the POSIX programming, we hereby list some. It is pretty simple to learn and deploy. There's no other license to pay besides the platform. It is really easy to operate, and the last but not the least, easy to debug. For those of you who weren't quite familiar with the shell scripting, I suggest to exercise the following code. Create a text file containing some easy-to-use commands. We're going to call it myprog.sh, and it's going to be our first and simplest of shell scripts. Once the connection is established with the Unix machine and the login phase properly accomplished, we're going to take these 4 steps for actually launching a script. In the first place, we need to create the file and put inside at least one Unix command. Thus, we're going to start with 2 of the most known commands, banner and date. They are quite simple to use. They do not need a lot of processing power, and their output is plain in sight. At the second step, we save and close the script file. We now have for our own use a small but functional shell script. At the third step, we're going to add execution attributes to our file. It is hereby visible the utility which can add execution permission. The difference between the 2 instances of the file details listing is clearly the X attribute for the owner of the file. And then we finally reach the last step, the most important of them all, actually calling our file. So at this 4th step, we're going to start running it this way. You can see its name being effectively written. For those of you who would wonder what the two symbols preceding the program's name are, I suggest to hold on for a second. We are going to clear out during the following lessons all the details regarding how a file is to be referenced. For the time being, all you need to learn is that this is how a script should be launched. There are several names for such an operation: launching a script, initiating a shell script, executing a script, or we could just say a script is ran off. We're going to meet again all these assertions during the next days, and they're all the same. The outcome of this operation is clearly visible on your screen, and we're going to keep in mind this effect during the next examples. In order to name this, we're going to use expressions like the execution of the script produces an output. The result of the script is this information thrown at the console's output. These are equivalent as well, and I would like you to use them thoroughly. The environment which the shell script executes within, which is quite important to us here, can have an impact on both how the script is executed and on the results that are produced. On a second view, the shell's operating context is in short a set of working parameters and settings which are managed in a series of special system files used for configuring the session startup. They can control both the interactive usage of the shell and the batch processing. For instance, the different methods used for the login can affect the environment, since the different authentication methods, which we're going to refer to as the login phase, have an opportunity to execute certain startup files, which are most probably scripts as well, and this is the actual working session context. These startup files can change shell features, command paths, generic shell startup variables, the way shell displays prompts, and the general behavior characteristics of the interactive shell. Although it seems all this is related to interactive usage, it can in fact impact the results of some shell scripts which are meant to work in the background. Given the fact that they are administrative assets, we aren't going to spend much time with them. However, you should be familiar with these files and their use because the following notes are provided just as a review. Usually the .profile file contains the main settings for the shell environment. This isn't the only configuration startup file. In fact, another similar file could very well exist under a different name, but is usually a standard name ending most probably in RC. The .shrc file can host some of the following. Most of them are covered in detail later in the course. Shell variables, aliases, meaning alternate words for user-defined commands, which can be used to invoke complex processes, and some low-level environmental settings, which are described by special words used for setting up the interactive behavior of the shell. The POSIX shell has a number of facilities to control the appearance of your operating console that can be turned on or off by using a very powerful utility, the set command. These settings are to be activated with this syntax, set-o, followed by a keyword associated to an operating option, respectively deactivated using the setup plus O option. Some of these options which we're quickly presenting here because we're going to have them later detailed are like this. The option ignore end of file makes the shell ignore the Ctrl plus D character as the shortcut for exit in an interactive session. The no clobber option prevents overwriting of files when using output redirection. And the last example that you're watching has an essential functionality. It alters the behavior of the output flow so that it sends to the console debugging related information. In all Although initially such control mechanisms were made available to operators to ease their interaction with the system, these commands are also perfectly functional within a script when scripting requirements make it necessary. What is actually going on when the Enter key is depressed? When a user types in a command and presses return, before the command line is effectively executed, the shell interpreter starts a process known as the interpretation of the code. We are going to learn that this is called a shell processing sequence, a name we're going to meet quite often. The same is true when the shell is running a script of several such commands. This sequence should be referenced for any command you're using within your shell scripts. The order of the processing is significant for understanding scripts. Your shell script can produce strange results if you try to do things out of order. A good understanding of the shell processing sequence hereby commented can help explain why you get some of the results that you do. So what are you going to see next highlights the major tasks that the shell performs on the behalf of the current system user, such as code interpretation and arguments in the command line, which you otherwise should explicitly write yourself. The shell first looks for special characters, meta characters on the command line. Each meta character is about to be interpreted by the shell as a separator. The meta characters separate the command line into tokens. The shell meta characters are space, tab, new line, the ampersand symbol, the semicolon, the round parenthesis, the pipe symbol, and others like them. At the next step, the tokens are checked to see if they are shell keywords, so they are processed as is. After some of them are identified, the shell goes on by checking the first word of the command against a list of aliases. If the word is in the alias table, substitution is performed accordingly, and the processing starts again with the separation into tokens like in step 1. At the fourth step, the shell performs substitution for the tilde. For the time being, all you need to know about is it's an operational shortcut to the current user's home directory. At the fifth step, the shell substitutes the values for any variable that is preceded by the $sign. This is also known as expanding variable stage. Then the shell substitutes any command expressions embedded within the command line by the proper call. Usually, these so-called expressions are enclosed within the $command notation. And here we are at the 7th stage. The shell evaluates an arithmetic expression enclosed in the $expression notation. Then, at the 8th step, the shell splits the command string into tokens again, this time using the field separator variable named IFS. By default, the IFS variable contains one of the white spaces characters, space, tab, or new line. The shell performs the substitution for the file name generation patterns, like the star symbol, the question mark, or the square brackets. The shell then removes any quotes from the result of all the previous processing and performs a command lookup in the following order: in commands, user-defined shell functions, and finally executable files by searching the command path, which is the path variable. The final step before execution is the initialization of any input-output redirection mechanism triggered by the usage of the greater than or lesser than symbols. Eventually, at the 12th step, this bunch of information becomes an executable command. The resulting command that is executed may be much different from what was typed in originally. This is where the power of the POSIX shell is evident. Short instructions to the POSIX shell can produce dramatic results. Before we moved on the next topic, namely the sub-process environment, a very important feature is to be noticed. POSIX scripts can be used in what are called nested execution schemes. In short, you can call a script inside another script and the number of nested levels is not limited in any way. We will learn to recognize these execution schemes, their building components, and the optimal way of managing them. Let us consider the following convention. In a nested script structure, the calling entity will be referenced as the parent and the called element will be known as the child. The main components of running POSIX shell process are the program code and the command arguments. The exact program code referred to as the text can be seen in the upper left box, hereby named the parent. What you see as the shell program code is the effective command string. The data, also known as arguments, are split into two distinct sections and are to be identified in the upper right side of the box as local data and environment data respectively. When a command is executed using the POSIX shell, a new process is started, referred to as a subprocess, which is responsible with carrying out the command. The resulting procedure described in the slide is known as the Fork-Exec sequence. Here is how things go. The shell, actually the parent shell, invokes a copy of itself as the subprocess. This is accomplished by invoking the fork system call. This is also known as the forking a new process. Thus, we end up with a hierarchy of processes where the subprocess is called the child process, whereas the caller is considered the parent process. The parent shell will wait while the child shell is running. All the local variables from the parent are also made available to the child. Meanwhile, the environment variables are admittedly reused as is. The child issues the exec system call to replace the program text from the parent, but then it will use for that its own copy of data, which will finally help it having its own valid code, possibly very different than the original parent's code. At this stage, the command finally executes within the environment of the child process. When the child process completes, the subprocess returns its exit status as an integer value back to the waiting parent process, which was in a waiting state during all this time. The parent shell awakens and stores this information in a special variable named the return code, which is available by using the $? variable. This one may be later used by the parent shell to determine whether the child process has succeeded or failed. A return code like 0 means one successful end. Any other value is returned instead of 0 means that there were problems in carrying out the command. As you will see, the POSIX shell provides a powerful set of capabilities that are ideally suited for working within the UNIX operating system. Its built-in commands, command history management, command line editing, aliases, functions, environment variables, a file name generation feature, and a powerful programming language make it one of the best choices for shell programming in today's UNIX operating system, at least when compared to other available UNIX shells.